Hi guys, Mr. C here with you. Today I'm going to do two videos. This is going to be part one of deriving the range equation. In this video I'm going to start and end on level ground. So let's go ahead and draw a picture of it. So here is me kicking a ball. I'm going to give it an initial velocity, we'll call it VI, kicked at an angle theta. Ball is going to travel up and down to the air. And what we're interested in is finding the range, how far it travels, and along the way we'll also find the maximum height it obtains, and we'll need the time it's in the air. Now, for this and for the second video, the key part of figuring out the range is understanding that the range is going to be the horizontal component of velocity times the total time that the object's in the air. And so for both videos, this one and the following one, when we do the general range equation, we're going to find an expression for the velocity in the horizontal direction, and we're going to find some expression for the total time that the ball's in the air. So, first off, for our ball, it was kicked with initial velocity VI at an angle theta. What we've talked about in class is that initial velocity can be broken down into two components, a horizontal and a vertical. We call the horizontal Vx, and we call the vertical VIY for initial velocity in the vertical direction. And the two expressions we learned were the initial velocity in the vertical direction is the initial velocity VI times the sine of the angle, and for our horizontal, it's VI times the cosine of the angle. So now we have the horizontal piece in our equation. We need to find some expression for the total time. So what we're going to do is we're going to figure out how long it takes to get from our start position up to max height. Because one of the things we know is at the max height, the vertical component of velocity is 0. And we're going to use that fact to find the time it takes to go up. Then, because we're starting and ending at level height, we know that the time it takes for an object to go up in the air is going to be equal to the time it takes to go down. And that'll allow us to say that the total time is going to be 2 times the time it takes to go up into the air. So let's figure out how long it takes to go up in the air. I'll write down some stuff that I know. I know that the initial velocity in the y direction is VI times the sine of the angle. I know that the final velocity in the y direction is 0. I'm going to call the acceleration gravity. And since the object is going up in the air, I'm calling this a positive velocity upwards. Just bear in mind when we talk about gravity, it's negative 9.81 meters per second squared. Just keep in mind the negative. And we're going to solve for the distance that goes up in the air. That'll give us the max height. And we're also going to solve for the time up. So first off, the distance rises vertically. We have VF, VI, A, and D. I'm going to go ahead and use the VF squared equation because there's no time yet. So we're going to use VFy squared equals VIY squared plus 2A dy. I'm going to go ahead and replace my A with a gravity, and just be aware because it's negative, put it in there. Go ahead and quickly do some math and plug in. My final velocity is 0 at the top. My initial velocity, recall, is VI sine theta minus 2g dy. Now I just quickly rearrange it, and I get my max height is VI squared sine squared theta over 2g. And there's an expression for the max height as a function of the initial velocity and the angle. So that's going to be pretty useful for finding the max height of any projectile. Now I want to find the time it takes to go up. So I want to find time up. I'm again going to use the 3 pieces of data I have, the VF, the VI, and the acceleration of gravity. This time I'm going to use the equation VF equals VI plus AT. And again, just because gravity is negative, I'm going to put that in right now. So again, at the top, the velocity is 0. My expression for my initial velocity in the vertical direction is VI times the sine of the angle. and go ahead and solving for time, I get the time it takes to rise to the top equals vi sine theta divided by g. And since on a horizontal plane, the time up equals the time down, we have the total time simply is going to be twice that, so 2 vi sine theta divided by g. Now we're at a place to actually calculate the range of the projectile. So recall, the range of a projectile is the horizontal component of velocity times the total time that an object's in the air. So now I'm simply just going to plug in my two pieces that I have. So my horizontal component of velocity was vi cos theta, and my total time that the object was in the air was 2 vi sine theta divided by g. If I go ahead and do a little bit of rearranging, I get range equals, let's do vi squared times, I'll do vi squared divided by g times 2 sine theta cos theta. And what I put in the brackets should stick out as a double angle formula. So recall that from trigonometry, 2 sine theta cos theta is equal to sine 2 theta from the double angle formula. So we're going to make use of that and rewrite the range as vi squared over g times sine 2 theta. And we have an expression for our range. And remember, this is for starting and ending on level ground. Now, the first thing that we talked about when we derived this range equation was how this equation proved that the maximum range for a projectile occurred when theta, our launch angle, was 45 degrees. Let's go ahead and show that quickly. So recall, the sine function has a minimum value of -1 and a maximum value of +1. And the minimum, and these occur when theta equals 90 degrees. So if we want our range to be maximized, we want this sine value to be +1. We want it to be the whole number, because otherwise it's going to be some number between 0 and 1. So the sine value is a maximum when theta is 90 degrees. Inspecting that, we're going to achieve our maximum value of sine, again, when it's 90 degrees. So 2 times an angle has to be 90 degrees. Therefore, our maximum angle theta is 45 degrees. And that allows us to show that the optimal launch angle starting and ending on level ground and neglecting air resistance is 45 degrees. So that's the range equation starting and ending on level ground. In the next video, we're going to go ahead and derive the general range equation when we start off of a cliff of some height. And we'll still neglect air resistance for now, but we'll get to that eventually. All right, see you next video.